Welcome to this discussion on a fascinating paper exploring cooperative human-object interaction in humanoid robots. The paper, CooHOI, Learning Cooperative Human-Object Interaction with Manipulated Object Dynamics, introduces a novel two-phase learning framework for training robots to collaboratively transport objects. What are the key challenges addressed by this framework, and why are existing methods insufficient?
The primary challenge is the scarcity of multi-humanoid collaboration data for training. Existing methods often rely on motion capture data, which is expensive and difficult to obtain for complex multi-agent scenarios. Directly training a multi-agent policy from scratch is also computationally expensive and prone to convergence issues due to the expanded action space. CooHOI addresses these limitations by leveraging a two-phase approach: individual skill learning followed by policy transfer. Can you elaborate on this two-phase learning paradigm? What are the specific techniques employed in each phase?
The first phase focuses on single-agent object carrying. We use the Adversarial Motion Priors, AMP, framework for imitation learning, incorporating object dynamics, bounding box state, and velocity into the agent's observation space. This allows the agent to learn to interact with the object effectively. The second phase transfers these single-agent skills to a multi-agent setting using centralized training and decentralized execution, CTDE, with the MAPPO algorithm. Crucially, object dynamics serve as a form of implicit communication between agents.
The use of object dynamics as implicit communication is intriguing. How does this work in practice, and what are the advantages of this approach over explicit communication methods?
When one agent interacts with the object, it changes the object's dynamics. Other agents observe these changes and adjust their actions accordingly. This implicit communication avoids the need for complex communication protocols, making the system more robust and scalable. It's more efficient and natural, mirroring how humans often collaborate without explicit verbal instructions.
The paper mentions the use of bounding boxes at the ends of long objects. Why this specific choice, and how does it relate to the single-agent training?
For long objects, focusing on the bounding boxes at the ends allows each agent to effectively treat its end as a smaller, independent object. This aligns with the observation space used during single-agent training, facilitating a smooth transfer of skills. It also simplifies the coordination problem, as agents only need to focus on their respective ends.
The paper evaluates the framework on various object-carrying tasks. What were the key findings, and how does CooHOI compare to baselines?
CooHOI demonstrates significantly improved performance compared to training from scratch, which often fails to converge. It achieves high success rates in both single-agent and multi-agent scenarios with various objects: boxes, sofas, tables, etc. The use of object dynamics as feedback is crucial for success, as ablation studies show that removing this information drastically reduces performance.
The ablation studies are important for understanding the contribution of different design choices. What were some of the key insights from these studies?
The ablation studies highlighted the importance of several key components: the use of standpoints to guide the agent towards the object, the inclusion of object dynamics in the observation space, the incorporation of reverse walking motions in the training data, and the initialization of the multi-agent policy using the pre-trained single-agent policy. Removing any of these components significantly impairs performance.
The paper also discusses limitations and future work. What are some of the key areas for future improvement?
A major limitation is the lack of dexterous hands on the humanoid robots. This restricts the types of objects that can be manipulated. Future work will focus on incorporating more sophisticated manipulation capabilities, active perception, and improved navigation to enhance the framework's generalizability and robustness. Also, exploring more complex collaborative tasks beyond simple object transport would be valuable.
Finally, what are the broader implications of this work for the field of humanoid robotics and multi-agent learning?
CooHOI offers a promising approach to training cooperative behaviors in humanoid robots, addressing the challenges of data scarcity and computational complexity. The use of implicit communication through object dynamics is a novel and efficient strategy that could be applied to other multi-agent tasks. This work contributes to the development of more capable and adaptable humanoid robots for real-world applications.
This has been a very insightful discussion. Thank you for sharing your expertise.